In this video, we're actually going to start the topic of much of our course, our pre-calculus course, and it has to do with functions, all right? In this chapter, we're going to focus on just general properties that can span any type of function that we may encounter in math. And then for the rest of the semester, for the vast majority of the rest of the semester, we're going to look at specific types of functions and some of their properties and things that are specific just to those functions. And so let's get an overview of functions to get used to things that apply to all of them. And with that, we have a couple of definitions that we want to look at. Our first definition is the definition of a function, right? And so we have the definition of a function. These are your textbook definitions. Basically, it is a function. A function is a rule that assigns each element in one set to a unique element in a second set. And so let's say that we have a set of x values, right? For instance, I have x sub 1, x sub 2, x sub 3, and x sub 4, right? And basically, a function is a rule, so that means I can place some rule that takes the elements, and I'm going to call that rule f, the elements of this first set, and we're going to assign it to elements in the second set. Let's call the elements in the second set that they get assigned to y sub 1, y sub 2, and y sub 3. And basically what a function does is it basically just assigns. It uses some formula or some rule to assign it, right? For instance, we can say that x1 gets assigned to y1, x2 gets assigned to y2, y3 gets assigned to y3. Now, note here, each of these elements are getting assigned to one element in this set over here. And let's say that x4 also gets assigned to y3, right? Each element gets assigned to one element out here over in the other set. Another way that we can think of this is that a function is a set of ordered pairs in which no two ordered pairs have the same first coordinate and a different second coordinate. All right, let's look at that, right? For instance, we have one set, which is our input into our function, and then we have another set that's our output, right? Which gives us pairs. And we're going to say the first set is the first coordinate and the second set elements in the second set are the second coordinates. That's why we use the word ordered pairs because the order matters, right? And so if I were to write this using ordered pairs, then I can use x1 comma y1 because x1 got assigned to y1. This is in the first set. This is in the second set, right? My next ordered pair will be x2, y2. Then we have x3, y3, and then we have, I did that incorrect, x4, comma, y sub 3, right? Because that one got sent to y sub 3 as well. And so basically what this means is if you look at the ordered pairs, x1, x2, x3, and x4 are completely different. And so this set of ordered pairs, no two first coordinates are repeated, right, in all this set of ordered pairs. Now, these are your textbook definitions. I like to think of functions in terms of inputs and outputs, right? You take some elements, you input them into your function, and then they get sent to some outputs. And so an alternative definition of a function, it is a relation. All right, let's make this a little bigger. A relation in which each input gets assigned to exactly one output, all right? So it's a relation in which each input gets assigned to exactly one output, right? So it's a relation. A relation is basically a relationship, all right, in which each input, I'm calling the x1, x2, x3, and x4 your inputs, and they each get assigned to exactly one output. Now, they can get assigned to separate outputs or they can get assigned to the same output like x3 and x4. As long as you don't see x1 getting assigned to more than one output, then you're a function. If you're not a function, you're what we call a relation. And basically a relation is any set of ordered pairs, right? And so an example of a relation would be something that looks like this. Let's say I had x1 and x2. And let's say I had, well, let's just make an x1 here. So for instance, I had x1 And let's say I had y sub 1 and y sub 2, right? Let's say x1 got assigned to x1, y1 and y2 using some relation, right? Then the set of ordered pairs here will be x1 comma y1 and x1 comma y sub 2. Notice here in this relation here, x1 repeats, which makes it not a function. And on this diagram here, we have two arrows coming from the same input value. And so this is not a function. It's just a relation, whereas this type of setup is a function. All right. Some information related to functions. These are two very important things, and these actually relate to both relations and functions. You can find their domain and range. The domain is your set of all first coordinates to your ordered pairs, and in math we usually use our input value as x when we're talking about function notation. So it's your set of all x values where your function is defined if you're talking about a function, or if just your set of first coordinates if you're talking about a relation as a set of ordered pairs. And then your range is your set of all second coordinates of your ordered pairs in your relation. And a lot of times in math, we use our output value as a y coordinate. And so you can think of it as your set of all y values. All right. So your inputs, x values, some people use the word inputs. And then y values, or some people use the word outputs. All right. Are your second coordinates and your first coordinates. All right. Once we know that something is a function, we usually write the y is a function of x. Now, sometimes we try to stay away from always using x and y because those are not always your variables, right? But I'm going to stay consistent with your textbook this time, right? Instead of using y as a function of x, you can always say that your output is a function of the input. That's one way that you can write it. Or you can say your second coordinate is a function of your first coordinate. And the notation that we use instead of using these words is we say that y is usually is replaced by an equal sign, and then we have f of x. All right. And so this is function notation here. Our input value goes here. I'm telling you what's my domain variable, my variable that represents my domain, like my x values, where my function is defined. I apply the rule f to that. Notice you can use any letter for f. Sometimes we use G, sometimes we use H, sometimes we use other letters. And then when you apply this function to your input variable, you get your output, which is y. All right. And so that's function notation. Let's look at some examples here. So let's say that we have these relations here. We have some equations, right? And so basically I said that functions are usually rules. Usually we use numbers as our input, and our output is going to be a number as well. We're going to focus on real numbers since we're working in the real number system. And so we can write things using algebraic expressions so that our rule is actually an algebraic expression, all right? So our function rules are algebraic expressions. There are other types of function rules that take functions as your rules, right? Are your inputs and your outputs. And so those are called functionals or whatever. But we're going to focus on our real numbers being our input, our real numbers being our output, and algebraic expressions representing the rules that send our inputs to our output, right? And so if I want to look at an equation and determine whether I have y as a function of x, then what I'm going to do is I want to make sure that each x value, that if I plug in each x value, I'm only going to get one output value. One of the easiest ways to do that, this is not the only way to do this, but one of the easiest ways to do this is to solve the equation for y. If you can solve an equation for y and there are not multiple equations that result, then it is a function. Y can be written as a function of x, right? For instance, this equation right here is already solved for y, right? It has y equals 4 over x minus 7, right? So no matter what x value I plug in, as long as it's defined, I'm going to get one y value. For instance, when you first started math and you started talking about graphing, right, you can plug in some values, right? So for instance, if I plug in 1 for x into my function, that means go into x, plug in 1, I get 4 over -6, right? I'm not, well, -2/3, right? If I plug in 2 for x, I get 4 over -5, right? And so no matter what x value that I plug in, if it's a real number, I know I'm going to get exactly one output, okay? So that makes this a function. In fact, usually when you see equations written like this, where y is on one side and algebraic expression that only involves your input variable, which is here x, is on the other side, it is considered a function. So I'm going to say yes, y is a function of x in this example. Now it says if it is a function, find its domain. So when we know we have functions, we can actually use function notation. I can replace y with f of x and write this as 4 over x minus 7. All right. I know it's a function, right? Now I'm going to go back to talk about this domain thing. I gave the definition of domain in terms of relations here. It's your set of all first coordinates or of the ordered pairs in your relation. When I'm talking about a function, it's the set of all x values or input values where your function is defined. All right, where your function is defined. All right, now when we talk about functions being defined, we got to look out for places where your function may not be defined, right? Where it may be undefined. And one place where it may be undefined is division by 0, right? So if I ever have a function, when I solve the equation for y, I get y on one side, everything on the other side, and I have an x in the denominator, then there's the potential for my function to be undefined. And the place where it's undefined is what makes my denominator equal 0. And so what I do here is I'll take that x minus 7 and I set it equal to 0 because we want to know what x values make that 0. Now, just to remind myself, I don't want the denominator to equal 0 because if it does equal 0, then I'm dividing by 0, so that's undefined, right? And so what I'm going to do is I'm going to solve this unequation or non-equation here. For x, I get x cannot equal 7. And so my domain is going to be all of my real numbers, right? So my domain is going to be all real numbers except x equals 7. All right. Now, that's one way that I can write this, right? Or I can write it in set notation. I can say that this is the set of all x, because that's my input value, such that x does not equal 7. That's an alternative way to write that, right? This is using set notation. Now I'm going to show you how to write this in interval notation, right? In interval notation, you got to think about a number line. All right, let me make sure you guys can see this. Yes. You got to think about a number line, right? If I were to put a number line, notice 7 can go on that number line because that's what x cannot equal. Whenever you want to skip over a value in your number line, you usually use an open circle if you don't want to include it. And then you shade in all the other values where where you want your solution to lie. So since I can use all real numbers except x equals 7, then my domain is going to start with negative infinity, right? Negative infinity is over here, up until I get to 7, comma 7. I'm going to use a parenthesis. It's going to be a union symbol, and then I start back right after 7 and go to positive infinity, which is over here. That's interval notation. Let's go to part B. It says 2 square root of x plus 4 minus y equals 3. What I'm going to do is I'm going to go through the process of solving for y, right? That means I'm going to subtract this whole term here, and I'm going to get negative y equals negative 2 square root of x plus 4 plus 3, right? Or you can say 3 minus 2 square root of x plus 4. I'm going to divide both sides by negative 1, and I get a positive 2 square root of x plus 4 minus 3, all right? And so since I was able to separate y on one side by itself and get my function, I get an expression with just x on the other side, I know, yes, this is a function, right? So I can say that this is f of x equals this thing right here instead of saying y, right? And so what we have here is that we have a function. So let's find its domain. Remember, we're going to be working in the real number system. So when I input a real number, I need to output a real number. Well, notice here, I have a square root, right? And so the thing about square roots is that if I input a negative number inside that square root, then I'm going to get an imaginary solution or an unreal or non-real complex number, right? And so what we do here, now here we knew that we couldn't divide by zero. We didn't want to divide by zero, right? Because that makes it undefined. Here, we don't want this to be a negative number. Or I can say I want the numbers that I plug in for x to be a positive or a zero number, right? So what I'm going to do here is I'm going to take whatever's under my radical, right? Notice I'm focusing in on what's under my radical, and I'm going to restrict it so it's greater than or equal to zero, okay? Now let's solve for x. I'm going to get x is greater than or equal to -4, and we have to remember that with inequalities, this is how we solve them. You solve them like equations. The only difference is that if you multiply or divide by a negative number, then you're going to have to switch the inequality sign. And the reason why we do that is because when you multiply both sides by a negative, what number was larger becomes smaller, and whatever number was smaller becomes larger, all right? That's why we flip the inequality symbol, all right? Now notice here, I set this greater than or equal to zero because I want to restrict my domain to only include these x values. Notice this was not under the radical and this was not under the radical, so it has nothing to do with my domain, all right? My domain restriction. All right, I'm gonna put this on a number line so that I can write this solution here. All right, I'm gonna put -4, I'm gonna zoom in on -4. Since that was an equal to, I will put a closed circle. Notice when we had an unequal, we use an open circle, right? And then I want values that are greater than -4, which are to the right. So my domain, I'm going to write it in interval notation. It's going to start at -4. And since I include this -4 with this closed circle and I have this equal sign, I use a square bracket. And I'm going to continue into indefinitely. So I'm going to go to positive infinity. So I can write that in set notation that way. Interval notation that way, or you can say it's the set of all x such that x is greater than or equal to -4. All right, we don't have to write that in words, okay? I think you will probably be writing domain this way here, just in case I wanted to give you that as well, all right? So to C here, I have x plus 2 absolute value of y equals 2. Again, I'm going to try to solve for y to get y and x on separate sides of my equation here. Right? So I have 2 times the absolute value of y equals, let's subtract x. Let's divide both sides by 2. So I get absolute value of y equals 2 minus x over 2. Remember, we want to solve for y. This is not solved for y. I have the absolute value on this left-hand side. Remember, if I want to remove the absolute value, I set it equal to the positive and the negative of what's on this side here. All right, so I get y equals positive 2 minus x over 2. Or y equals -2 minus x over 2. All right, if you want to write it as one equation and put plus or minus, that's perfectly fine. But notice here, when I plug in one single x value, I have to plug it into both of these equations, right? For instance, if I plug in x equals 1, right? So like if I did me a table of values, I plug in 1, I have to plug it in both of these equations, right? So I'm going to actually get, well, we'll plug in 1 here. I'm going to get 2 minus 1, which is 1 over 2. And then when I plug in 1 here, I'm going to get 2 minus 1, but that's a negative out front. I get -1 over 2. So here I have one input getting assigned to 2 outputs. This does not represent y as a function of x, right? And so we don't have to find a domain here. All right. So try to solve for y, and if you end up with multiple equations, like a plus or minus or something of that nature, then you know for a fact that you don't have y as a function of x. All right, this is looking at equations. We can use what we call the vertical line test in order to help us determine if y is a function of x when we're looking at a graph. All right. Again, it says that, okay, it is a function as long as there are no x values that repeat when we have a set of ordered pairs. And so if I could draw a vertical line, or if I could find a vertical line that passes through the graph of the function at more than one point, that means, remember, your vertical line is like this, and if it passes at more than one point, That means, your vertical lines is always x equals some number, right? And so let's say that this is in my xy plane, x equals, this number right here was 3. And this is 1, 2, 3. Then this ordered pair would be the 1.13. This ordered pair, sorry, that would be 3, 1, x value first, y value second. And this would be the 0.33. Then if you have a vertical line and it passes at more than 1 point, then the first coordinates repeat themselves, so it cannot be a function. And so when I look at a graph, for instance, if I look at A, there is no vertical line that I can draw on this picture or this graph here that's going to touch that function at more than 1 point, right? And when that happens, we're going to say, yes, it is a function. However, in part B here, my y-axis is actually a vertical line, and it crosses this vertical line at exactly 2 points, no matter where I go, right? Unless I'm tangent over there, right? And so this one is not a function, right? So vertical line test, just see if you can draw a vertical line and it only touches at 1 point. Any vertical line you can think about, and if it can only touch at 1 point, touch that vertical line at 1 point, then it is considered a function. All right, let's look at example 3 here. It says determine whether the graph represents y as a function of x, right? You got to think about the vertical line test again because we have a function. Now, this is a line segment. So through this line segment, no vertical line can be drawn that would make that a function. I'll say that more than 1 point. This is a horizontal line. So this is the line segment. It's not vertical, right? But a vertical line will only pass through all of those points at once. Same thing here for this line segment, same thing here for this line segment, and same thing here for this line segment, all right? So if I look at the line segments individually, we know that it looks like a function. Our problem is in the areas where these line segments overlap. Notice here, I have an open point here at the point 4, -4, but I have a closed point here at the point 4, -3. So and basically what I'm saying is that my function takes on the value of the closed circle, right? So if I were to draw a vertical line, it will only pass through this graph here at 1 point, all right? It will pass at the point 4, -4. This open circle is saying that I'm getting close to this point, but this point right here is actually not a point on my graph. Now, this scenario happens at each of these values where my line segment ends and the other one begins, right? I have a closed circle here and an open circle here, so that makes it a function. That's okay when we have a function. And then at 4, 1 versus at 4, 2, we have the same scenario. My function takes on the value 1 at x equals 4, and this is just an open circle to say my line segment ends right before I get to that point. And so this does pass the vertical line test, and so yes, it is a function. Okay, yes, it is a function. The only way for it not to be a function is if we had 2 closed circles. So if that was closed and that was closed, and I did my vertical line test, it would not be a function because my vertical line would pass through this point here and this point there. And that is not the case. So we have a function. All right. Now that we know that it's a function, we're going to state the domain and range. And notice here I put of the function. Lord. Okay. All right, so the domain is your set of all x values where your function is defined, all right? You got to think about all the x coordinates of your ordered pairs, right? And so what sometimes I like to do is I like to shade in my x-axis and for my domain and shade in my y-axis for my range. And by shading in, basically I look at my function, right? So my function starts to the left. There's no endpoint, so I know my function doesn't continue to the left of -6. But what I'm going to do here is I'm going to look at these points, right? I have a point at -6. All right, I'm going to shade in my x-axis. And all of these points on this line segment until I get to -4 have x coordinates that's between -6 and -4, right? Now, if I were focusing on this, I would use an open circle here at -4. However, this line segment starts to have a closed circle at -4, so I can go ahead and close that in, right? And so all of these x values between -6 and -4 are in my domain. In fact, since I have part of my graph from -4 to -2 with that line segment, all of these x coordinates are in my domain. And notice at 2, I have that point there. And notice here with this line segment, they have x coordinates between 2 and 4. and I close that in for this point here. And this one starts, and all of these points on this line segment have x coordinates from 4 to 8, and I will close that up. And so my domain just includes all of my x values basically from, so I'm going to say my domain is from -6 to 8. All right. Now I'm going to do a similar thing, but I'm going to focus on my range. All right, so I'll go from bottom to top, right? My lowest point on my graph is this point right here. It has a y coordinate of -5, so I'm going to put it there. All right, all of these points on this line segment all the way include all the y values up until I get to -4. But at -4, I have to have an open circle because I don't include that. It has an open circle there. So the values from -5 to -4, not including -4, are included in my range. Notice this is a perfectly horizontal line. So all of the points on this line segment have a y value of -3. So I'm just going to put a closed circle there. Notice I don't have any points on my graph that have a y value between -4 and -3, right? So I'm not including those values in my range. So I'm going to start writing my range here. I'm going to have a -5. Since that's a closed circle, I include the -5. And I go until I get to 4, but I don't include 4, so I use a parenthesis. Then I'm going to have a union here. And then notice this is a single point. Whenever we have set notation that includes a single point, we have to use our squiggly brackets. I know they probably have a different name. I just call them squiggly brackets. And I have that there. Let's get the rest of our range, right? All the points from this line segment start at -2 and include y values up until I get to 1, and I include 1. And so as I'm going to put another union here for another set, I start at -2 with the open circle, so I use a parenthesis. I go until I get to 1, use a bracket, because that's closed. I skip over 1, and I go to this y coordinate. Notice it is open. Y = 2 is open. And I use all the y coordinates until I get to this point, which has a y value of 3, which is closed. So I go union from 2 open to 3 closed. And so that would be my range. The last two topics are related to each other. This is an important calculus topic because it has to do with rates of change, which is the topic of calculus. And so we will revisit this concept as we go through studying calculus. All right. So average rate of change, right? We saw that your slope was the same thing as a rate of change. All right. Your slope of a line is the exact same thing for rate of change. They are synonyms. Okay. So if you didn't know that before, then we know that now. The slope of a line is constant. And so we can pick any 2 points on a line in order to calculate the slope. Well, when we have a function that is not whose graph is not a line, that means it's nonlinear, then we say that we can't find the slope in the normal way, or a representation of the rate of change using exactly, right? So on the slope of a line, I'm sorry, is constant. You pick any 2 points, you can find that slope, and it's going to be the same every single time. When you have a nonlinear function, if I pick 2 points that are over here, for instance, the rate of change of my function is going to be slightly different from picking my, doing the rate of change between these 2 points over here because I have a nonlinear function. All right, and so we use, instead of slope, we use what we call average rate of change of a function, and we always have to do it specific to a specific interval because depending on the location in which we want a representation or an estimate of rate of change, it's going to be different, and that's unlike for a line. And so I'm going to pick 2 points here. I'm going to call it the x coordinates to these 2 points, x1 and y1. Sorry, x1 and x2. And so their functional values are going to be y1, and this one has a y value of y2. Since this is a function, we could have said that this is f of x1, and we should have said that that's f of x sub 2, all right? But average rate of change is basically the slope of the line that passes through those points, right? So I don't know the rate of change of the function, so I'm going to use the actual slope of the line that passes through those 2 points in order to give me a representation of the actual rate of change of that function, right? So if I draw the line that passes through those 2 points, notice it's not the same slope. If you can, I covered it up. I wonder if I can make this smaller. So you can see that my rate of change of my function is changing as I go from x1 to x2 versus when I'm using the slope of this line here. And so the average rate of change is actually the slope of that line. And remember, our slope is given by y2 minus y1 over x2 minus x1. Or you can use the formula f of x2 minus f of x1 all over x sub 2 minus x sub 1. That's your average rate of change, and it's basically the slope of that line that passes through those 2 points. I said all that to say that, all right? A slightly different concept is what we call the difference quotient. Now, this is really getting into calculus here, all right? A difference quotient is an alternative way of computing the average rate of change of a function, and the alternative way is the average rate of change of your function as the function varies from x to x plus h, right? And so instead of going from x sub 1 to x sub 2, we're going to go from x, all right? And so let's say that we're going to go, the distance between where you were and where you want to go is h units, then this is going to be x plus h, all right? And so if I get my points here, and this is y equals f of x, then when I plug it into my function, I get my y coordinate. This is going to be f of x, and the y coordinate here is going to be f of x plus h. And so my difference quotient, it equals average rate of change, which I'm abbreviating with AROC. And if I use that same formula, right, if f of x2 minus f of x1, well, f of x2 is f of x plus h, f of x1 is f of x sub 2 is x plus h, and f of x, and then x sub 1 is x. Notice here the x's cancel. And we get this formula here. So our difference quotient is equal to this formula right here. This is something that you have to memorize. It basically comes from your average rate of change here, which you have to memorize as well. Let's look at this last example in this video. It says let f of x equal x squared minus 2x. Find the average rate of change from a equals 2 to b equals 5, right? And so this is like saying x sub 1 and x sub 2, right? And so I'm going to go ahead and do that, right? And so I'm going to, until I remember or memorize my formula, I like to use f of x2 minus f of x1. If you want to use y2 minus y1 over x2 minus x1, you can, because that's probably what you remember from your slope formula. But now that we know functions, I'm going to use function notation. And so I have f of 5 minus f of 2 all over 5 minus 2. And so basically, I'm going to come off to the side and do some scratch work. I'm going to put 5 in for x, right? I get 5 squared minus 2 times 5, which is 15, because that's 25 minus 10. And then f of 2, that'd be a 2 squared minus 2 times 2, which is 0, right? And so my average rate of change will be a 15 minus 0 over 3, which we get as 5, right? It says find and simplify the difference quotient, right? So my difference quotient, I'm going to abbreviate that with DQ. That's f of x plus h minus f of x all over h, right? And so I'm going to have, okay, my x, wherever I see an x, I'm going to have to substitute x plus h there, right? So it's going to be x plus h squared minus 2 times x plus h. All right, this is coming from this first term here. My second term is f of x, which is x squared minus 2x. You don't have to use brackets. I'm just using bracket. It's just a grouping symbol. It's nothing special about those brackets there, all right? It's just a grouping symbol. And so since I have that there, now all I have to do is simplify, right? Well, and I wrote something incorrect, did I? No, I didn't. And so I'm going to have an when I multiply this out, remember this part is x plus h times x plus h. Do not say that that's x squared plus h squared because you'll be wrong, right? And so what I have here is going to equal, I'm going to multiply that out. X times x is x squared. When I multiply x times h and then this h times x, I'm going to get 2hx. And then when I do the last, I'm going to get plus h squared. I distribute this negative 2, so that'll be a minus 2x minus 2h. And I distribute this negative here, minus x squared plus 2x. All of that is going to be over h. Now, I can simplify some things, right? Because this x squared cancels with this x squared, this negative 2x cancels with that positive 2x, and I'm left with a 2hx plus h squared minus 2h all over h. Well, since I have a monomial in my denominator, I can divide each of these terms by h, and when I do that, the h is going to cancel here, so I'm going to be left with 2x. One of the h's is going to cancel there, so I'm going to be left with h, and the h cancels there, I get 2. All right, and so this is your difference quotient. All right, I know this video is getting a little long, so I'm going to stop here, and I'll see you next time.